Hello, my name is Fastier-Wooller, and today I'll be presenting our work on low-power static and dynamic tactile sensing using In-Situ Fabricated PVDF-TrFE E-Skin as a part of IEEE Sensors 2021. Today I will be presenting a few brief topics from our work submitted to this conference. However, before I go on, I'd like to give a minor introduction to each of the points in here, namely our interest in piezoelectric sensors. The piezoelectric materials are quite interesting in their properties and performance as tactile sensors. Though piezoelectric materials tend to be overlooked in some applications due to the frequency requirement to generate a reliable signal. The piezoelectric mechanism itself is well known for the ability to perform ultra-fast and high sensitivity measurements. They are also known for their low power applications and even for power generation. Generally, crystalline materials are used. However, some polymers also exhibit similar properties, such as PVDF. We are interested in the ability to accurately and reliably use the benefits of piezoelectric materials, while also addressing the inability to measure static forces, and to then apply them in robotic tactile sensing as a more complete system. Through some rational design and fabrication considerations, we have proposed a tactile sensor device and are still currently working towards improving results and performance. I will cover what I've mentioned here in more detail over the following slides, namely design, sensing principle, the materials and fabrication, our results, and ongoing work. Firstly though, here are some of the common shared benefits and differences between piezoelectric and capacitive sensing devices. As mentioned previously, due to the mechanism of charge generation, piezoelectric devices are capable of low power applications as they generate an output signal with no required excitation voltage. The response time for piezoelectrics are incredibly fast and capable of distinguishing very minute signals and changes in pressure. This is excellent for applications that desire rapid identification of a response signal. However, piezoelectric devices are incapable of measuring static loads, which will be covered again soon. Before that, we must address the proposed design and structure of the device. Based on the requirements of the application for tactile sensing in a robotic gripper, there is a need for force or pressure measurements. Available to us is a Baxter research robot and his parallel gripper attachment. We expect to see a maximum applied gripping force of about 11 newtons. We also expect the need to measure both static loads and dynamic loads during simple tasks such as pick and place or other physical interactions. Additionally, there is an interest in vibration and other effects caused by motion of the arm or gripper during these tasks, which gives more reason to pursue piezoelectric sensing methods. To satisfy the requirements, we have picked materials that are strong and versatile in their flexibility and ability to conform to a curved surface. High sensitivity and performance is also of great interest. As such, we have chosen PVDF-TrFE to be electrospun into micro nanofibers, and this will be discussed a bit further on. Using the electrospinning process, it is possible to reduce the complexity and cost of fabricating the sensor, the structure, and adhere it directly to the sensing surface, removing the need to meddle with tricky adhesion or microstructuring techniques on the surface of the end effector. The proposed sensor uses a piezoelectric material as a dielectric between two conductive electrodes. This forms a capacitive structure that is sensitive to physical deformation or change in distance of d. This allows us to reliably measure static pressures. The PVDF fibers also generate a charge under the same force, dependent on time, to give us a voltage reading that is highly sensitive to dynamic pressures. Ideally, we are aiming to measure both of these signals simultaneously. However, in this presented work, we have presented the two signals separately. The structure of the end effector is a custom-made hollow PDMS fingertip designed to improve the deformation at low pressures and give a soft, more finger-like feel to the gripper. We perform this by 3D printing a mold and filling it with PDMS. As mentioned previously, we have electrospun a device to the surface of the end effector. This process primes the PVDF to a usable state as a piezoelectric and allows us to make it porous enough to perform well as a capacitor. Basically, this process serves to conform the sensing material to the surface of the end effector, polarize the material to be used as a piezoelectric medium, and provide a porous, fibrous structure to increase the capacitive sensitivity, while still remaining relatively simple and easy to perform and low cost. In this work, the sensing layer was fabricated in a 15 kilovolt field, 15 centimeters from our finger, rotating at 1800 RPM, with an estimated thickness of under 100 micrometers, which helps it conform to the surface under deformation. The electrodes are positioned before and after the application of PVDF. A conductive fabric tape was used as the electrode, as both electrodes, and is applied to the surface of the PDMS effector before the spinning process begins. When the device is finished spinning and the second electrode has been attached, a conductive silver epoxy is used to make the appropriate connections to wires for interfacing with the circuit. A final protective layer is also applied to the outer surface of the sensor. Here we can see the fabricated sensor with a protective layer on the surface electrode. The following slides will cover the method, data, and improvements. The experiments were performed using the Baxter robot's parallel gripper to grip and release an insulated wood block. To provide stable and uniform gripping motions, the gripper was mounted to a platform. This assisted in reducing discrepancies between each grip cycle caused by jittery movement and varied positioning of the gripping apparatus. This is a schematic view of the setup for clarity. Cycle testing was performed with 5-second intervals for both capacitive and piezoelectric measurements. For these tests, the gripper was configured to grip at 100% velocity and strength. Here we can see some excellent repeatability in capacitive measurements, approximately 7.5% change in capacitance under an estimated force of 11 newtons. The piezoelectric effect shows a semi-consistent response of approximately 300 millivolts, compression and release. We can see a point here where the signal has both compress and release, which is believed to be impacted by the deformation of the PDMS effector. One of the problems with this method of measurement is the alignment of data due to the separation of capacitive and piezoelectric measurement methods. Here is some of the data from the previous slide that has been aligned to show points of interest or grabbing events. A rising signal shows grabbing, where a falling signal shows releasing. Another issue with using this method is the discrepancy of sampling frequency seen here. Capacitive measurement systems tend to prefer accuracy over speed, whereas the voltage measurement is easily measured at higher sample rates. This can cause problems with aligning data and can introduce delays into any system that may use their kinds of measurement. Faster sample rates for capacitive measurements are possible and are currently being tested. However, we are more interested in the combination of these signals using a single sensing circuit, which would eliminate the need for aligning data. Of main interest is the possibility of improving the repeatability of the piezoelectric signal. High sensitivity and incredible response times can be seen, but some inconsistencies in data are also apparent in this data set. More recent experimental work has shown repeatability improvements and will hopefully be published soon. Also, there is sensor fusion, which involves the cumulation of multiple sensors or sensing data into a single signal. Ongoing work is being performed to find a solution capable of measuring both effects simultaneously and output a single or multiple signals without interference. If you have any questions, ideas, or there is something you wish to discuss with me, please contact me. Thank you very much for your time.